Third grade. Austin, third grade. We have been talking about simple machines, right? And we have worked on all kinds of different projects with simple machines. Today is the grand finale. What does a grand finale mean? Abby.
A grand finale means like something big for the ending.
Something big for the ending. We save the best for last. What we're going to do is we're going to take everything we know about simple and compound machines and we are going to do something big. Okay, I need your eyes looking right here and I need you to help me with your voices, your soft voices. Read this with me. Fletcher, ready? Animals in both the wild and in the zoos can fall into ravines or other deep pits. Rescuers need to be very careful when helping track animals like horses, lions, and elephants. These animals can be very large and require the use of machines to provide enough force to lift and rescue them. Stop. So far we know that we're going to be building a big machine. What is the problem? So far, there's a tiger stuck in the moat. Let's keep going. The largest animal on land is the male African elephant, which can grow up to 10.5 feet tall at the shoulder and can weigh up to 15,000 pounds. Stop right there. So what do we know about the machine that we are going to need to design? What do we need to know, Austin?
It needs to have a lot of armor and it has to have strong. It needs to be strong.
It needs to be super strong. We do know that. You have learned about effort, my turn, and resistant forces in simple and compound machines. You also investigated magnets and how they interact with objects that are not touching. The design problem you now face is to design an animal rescue device. A what?
Animal rescue device.
A model is often smaller than what is used in real-life situations. Models are used to test designs. So tell me why we're only building a model.
Because if it was,
Thank you, Austin, for raising a hand.
because if it was real, then it would take more time and it would take a lot more money. And it's only just an experiment and we don't know if it would actually work or if it wouldn't.
Okay, so we, of course, cannot build a real life machine. My turn. That can save this tiger. But we know that oftentimes engineers and scientists build models as an example so they can go through the engineering design process. Now, the first step in our engineering design process is what? Thumbs up, tell me. Thumbs up. Maylee, hit it.
The engineering design process,
What's the first step?
I think it's imagine.
The first step.
Ask.
Ask. What do we ask?
How do you do these stuff and how do they work?
What do we ask? Drew?
What is the problem?
Okay, at 3, I want you to say, Mrs. Carlson, what is the problem?
Miss Carlson, what is the problem?
I'm glad that you asked. After we read this story, someone raise their hand or give me a thumbs up and tell me what the problem is right now.
The problem is that the tiger is stuck in the deep pit and he can't get out of it.
The tiger is stuck in the moat and he cannot get out. That's the problem. Check! We've done that part of the engineering design process. Okay, what do we need to do next in the engineering design process, Austin?
Make a model.
Not next.
Explain to a group what we need to do, figure out what we need to design.
Imagine.
Imagine. Okay, so now we have to think about some constraints and some problems we have some rules or expectation Ms. Carlson and the engineer design team have to solve our problem. So this is what you're going to be expected to do. Think and look carefully. Your team will design, build, and test a device to rescue a trapped tiger. The device, Davis, must safely lift the animal for at least 4 inches and set it down in a safe area away from where the animal was trapped. How can I know once I start building what 4 inches is exactly? What tool can I use?
Ruler?
I can use a ruler or a measuring tape. You must include a magnet in your design. Thumbs up. Do you remember we used magnets and did some testing and exploration with magnets?
Yes.
Guess what? Today we get to use what you know about magnets. And your contraption, your machine, must have a
Magnets.
Okay? Your design must include a compound machine consisting of at least 2 simple machines. So remember, we've talked about all the simple machines we know, like a
Pulley.
pulley,
Pulleys.
like a
Lever.
Screw.
like a
Lever.
Wedge.
like a
Axle.
and we have to at least put 2 together to make a compound machine to rescue this tiger. Are you up for the challenge?
Yes.
There's more. Your design must include a compound machine of at least 2. Can you do more than 2?
Yes.
A harness for the animal must be created that safely supports the animal and does not pull on the animal's tail, legs, or head. So, you are going to have a tiger. Abby, will you quickly go get me one of those tigers on those trays?
Yes, ma'am.
Super quick. You are going to have, wait till I finish and then you can ask any question you need. You are going to have a tiger, and remember, this is a model. Thank you. This is a model. So, this is going to be our tiger. Would our tiger in real life be much bigger?
Yes.
We are going to use everything that we have learned about simple and compound machines. Okay? Now, our main goal is to save this tiger, but we also have to think about force and motion and stability and balance. Okay? So for us to think like scientists and engineers, we have to think about those things. Okay, so we've asked the question what the problem is. We've imagined. Now what should we do?
Plan.
We should plan. Your job right now, I'm going to give you a couple of minutes. There's a square Davis right here on your planning sheet. Okay? This is going to be your map. Because guess what? Engineers, Fletcher, don't just come with bricks and stones and hammers and nails, Fletcher, and start building. What do they have? A plan or a sketch or a blueprint. So, even though you're going to be working as a team, I want you to spend a couple of minutes and draw out a quick sketch that's going to include a magnet and at least 2 simple machines. Are there any questions right now? Austin?
Can we make does it have to be like, can it, for the tiger, can it wrap around on its stomach or can it drop down and connect itself?
Both.
Okay.
Okay. The harness or the string just has to keep it safe because we don't want to pull a tiger by its tail or its legs because that will harm the tiger. Yes.
So if we, for the contraption that is carrying the lion back up, can it walk into it from like a trap?
That's
it would walk
a great
into
question. You need to be able to get it.
it. Okay.
Okay?
Then I know what.
You have a great idea. Okay. So I want you to super quietly, go back to your space and spend a few minutes. Come get your planning guide first. Put it out in the building. And get to your sketching.
Yeah.